So I'm going to start now.
Okay.
So tonight I'm going to talk about a reassessment of the chronostratigraphy of the late Miocene C3, C4 vegetation transitions, which happened in the Miocene. And I want to thank my contributors, Sarah Feekins, Hannah Liddy, and Gali, Feng, Tierney, Miao, and Warney. And they were contributors to this project. So what I'm going to talk about is, first of all, how I came to go to Pakistan in 1977 as an undergraduate, and then about the C3, C4 vegetation shift in the Miocene, and how that relates to a late Miocene carbon isotopic shift in the marine realm. How do they relate, and what do they mean, as far as we can tell? So in 1977, I went to Pakistan for the first time with the Yale group, and we went to the Patwar Plateau of Pakistan to study the Shawalik sequence. So what we did, my first project was to study these big sandstones that you see here. And these are used to tie together all the fossil locations that the Yale group were finding, and they were using these big sandstones as time horizons, so they were considered to be instants of time. And that the question was, were they? And so some of these had magnetic reversals associated with them. And so I would walk along these canyons to take samples at first along these big sandstones. So sampling across the same sandstone in many places across a region of, I don't know, like 50 kilometers, and to decide whether or not the sandstones were isocronous in fact. And so that was the first project, which with the help of Kay Berensmeyer, we published. And so this is the trace of one of the sandstones that we call the U sandstone. And I took little sections across this sandstone in these places, and tracked the reversal. So how we took the samples was the method developed by the Dartmouth Columbia team, where you hack off weathered material to get fresh in situ material, and then shave off a flat surface, mark the strike and dip on the surface, and so it's oriented in space, and then measured it in a magnetometer, not like this, but this is the one that I have now at the Scripps Institution of Oceanography, where you measure the three vectors of the magnetization along an oriented, relative to an oriented arrow, and then you can get the direction relative to north to see whether it was pointing north or pointing south. And then as part of this experiment, you progressively demagnetize the vector. So here's a picture of, this is a stereonet. So this is north, the outer rim is horizontal, and this is vertical. So this direction is slightly to the west of north and about 50 degrees. And as you demagnetize the sample, the vector goes to the origin. And so this is a 3D plot of these same directions where, and then you determine a direction that is characteristic of that particular specimen. And then you can look at the directions from several long sections here, and this would be a normal direction, so that the magnetic vector is pointing north and down, and these, by convention, open symbols are up, so these are south and up, and so this would be, these would be normal, these would be reverse, and that's how we do the magnetostratigraphy. So in my undergraduate work, this is a figure from K. Berensmeyer in my paper. This was the sandstone that I showed you the trace of, and these are the sections through it. So this is 50 meters. So these open symbols are interpreted as being reverse, so the magnetic field was pointing in the opposite direction. And these are normal, and these are reverse. And so there was this reversal somewhere under this particular sandstone. And you can see that it stayed under that sandstone, except here it came very close. And you can see there is, like if you found two fossil beds here, and we're using the top of the U sandstone as a reference, these would appear to be the same age, but in fact they can't be, because these are in the normal zone beneath this reverse zone. So there had to be some time difference between these two. But in general, these sandstones were pretty isochronous, and I believe they are isochronous, just big flooding events. And these would be the red beds in between the different sandstones. So that was my undergraduate work. Then John Berry of the Yale group, who's now at Harvard, he suggested that I sample along a couple of longer tracks. And so I did a few very long and densely sampled sections along, and so this would be the older part and the younger part, because this is a syncline. And so I sampled this one. This is Ratakas, and this is Kalialkas, which I'll show you later. So the first thing that I discovered sampling this, these longer transects, is the magnetostratigraphy, which had been done by the Dartmouth group, was sampled at a very low resolution. And so this was the original sampling by Barnt et al. And they had this big long normal with a few short reversed intervals in there. They correlated this big long normal event to what is known as it was known as Epic 9 and is now referred to as Cron C5N. And then I sampled a parallel section to it at a much higher resolution, and found not just these. I never did discover this reversed interval, but instead of these, I found much more reverse. And so the conclusion was that this magnetostratigraphy had been entirely misinterpreted because it was so undersampled. And so the revised correlation is this one, is the Ratakas section. And so this was tied to this interval. This is the epic numbers in the old time scale. And these are the dates at the time. So this would have been 10 million years old down here. And this would have been more like 8 million. And so all of the fossil horizons that were associated with this is the U sandstone I showed you before, and this is that reversal that we sampled in detail. And the fossils that were associated with U sandstone, their date changed by a lot, became much younger by more than 1 million years. And since a lot of the hominid fossils, hominoid fossils, hominine fossils, whatever you call them now, were associated with this sandstone, this was a new date for what was then called Ramapithecus, and now is understood to be Shivapithecus's wife. So that was the story of that I spent a lot of time as a graduate student with Neil Updike. So and so that's then I also measured samples from this section called this was Ratakas. This is the Kolyalkas, and we published this paper, which extended the section further up in time, up to about what was understood at the time to be about 6 million or 6.5 million. And then after that, the Jay Quaid and Turi Serling and others went and sampled this section, the Kolyal section, as well as many others, and measured the carbon isotopes, the C13 ratios, delta C13 ratios in nodules found in the paleosols. And this was their first publication, 1989. And the red dots here, this is against age. The red dots here are from the Kolyalka section that I just showed you, which just barely caught this transition from between this isotopic signature with an average of around -11 to this one, which is 0 or more positive numbers. And these isotope values are tied to plants that are called C3 photosynthetic pathway. They include cereals like barley, oats, rice, wheat, alfalfa, cotton, sunflower, eucalyptus, soybeans, potatoes, beets, and tend to be trees, tend to be C3. And then, but you can see there was this profound shift in vegetation to what are called C4 plants, which are sugarcane, maize, sorghum, grasses, and amaranth, and so on. And so it was interpreted as a profound vegetational change from trees and shrubs to grasses. And so this caught the attention of many people. These guys are now quite famous, and so it was picked up across the paleoclimate community, including a guy named Jim Zakos, who's at the University of California in Santa Cruz, and he, in 2001, collected together all the delta 018 records he could find from the deep sea cores and plotted them on a time scale. And this tells the story of the Cenozoic climate. So in the Eocene, the climate, these delta 018 numbers suggest that there was absolutely no ice, sea ice, no ice anywhere, no cryosphere on the Earth, and the Earth was quite warm. We know that because there were alligators and turtles up near the North Pole. And then the climate began to get cooler. And here's the Oligocene first glaciation of Antarctica. And then it warmed up again in the mid-Miocene optimum. And then started to get colder, and then this is when the northern hemisphere ice began to form about here. And so what was going on in the rest of the world, he's tied in the Asian monsoons intensifying and a lot of climatic events throughout the Cenozoic. There were some tectonic events happening as well. And then he has biotic events, and one of those biotic events was the C4 expansion, of grass expansion, which happened on the continents. All the rest of these data are marine. And so he tied this to an increase in the Asian monsoons. And these are marine records, and so there's also a little blip in the Delta C13 record at about the same time. This is 8 million. So before I told you that transition happened at around 6 million, according to the timescale at the time. And what this blip in Delta C13 is something actually called the Late Miocene carbon isotopic shift, which was discovered in marine records. And so it was never really tied directly to what was happening in Pakistan that Jay Quaid and Terry Serling found. So I got interested in this at some point, way after Quaid and Serling and others were working on it. But my interest is, I do magnetostratigraphy, among other things, as you know by now. And so I was interested in the timing of these things and whether we could actually tie these two events together using independent chronologies. So the question is, was this a global event, this late Miocene carbon isotopic event and the C3-C4 vegetation transition? And then you might ask, well, why do we care? Does this tell us something about the monsoon, like Jim Zakos suggested, or does it tell us something about CO2 in the atmosphere? I mean, as you must be aware, everybody's worried about the CO2 in the atmosphere. It's now at record highs for the Pleistocene. It hasn't we have not had this much CO2 in the atmosphere since the Pliocene. And so the reason why C3, C4 grasses might be telling us something about PCO2 or are related to PCO2 is, in fact, C4 plants prefer lower CO2 in the atmosphere, and C3 plants prefer higher CO2. They are also, these vegetation, of course, are sensitive to hydrology, you know, how wet things are, and temperature. But people have zoomed in on the CO2 story. And the reason, I mean, this guy, Joe et al. In 2018 published a paper called C4 Photosynthesis and Climate Through the Lens of Optimality. And the story here is these are maps of models, predictions from whether C3, which are in these green colors because they're forest and trees, and they like wetter environments, versus C4, which are like drier climates, and lower CO2. And so here we have a map predicted for the condition where the atmosphere, which is uniformly mixed with CO2, the atmosphere being 600 ppm. Right now we're above 400. And so if you have high CO2, you expect that the region of these brown colors, the C4 plants, to be restricted. And then as the CO2 comes down to, this is the Pleistocene number, you can see that C4 has expanded everywhere across the United States, all across Asia, Europe, Southern Europe, East Africa and Northern Africa, South America, Australia. So as CO2 goes down, the only variable here was CO2. So CO2 going down enhances C4 vegetation. So did the expansion of C4 in this part of the world, which is where we're looking, does that indicate that CO2 levels came down and then C4 plants took over? So that's a question for the Miocene. But the story is more interesting than that. And because C4 plants themselves draw CO2 out of the atmosphere. And so C4 plants, according to this paper, which was published in 2008, it's based on experimental farms in Minnesota. And they had different greenhouses with different CO2 contents, and they found that C4 grasses and legumes increased soil carbon accumulation by 200 to 500%. Just amazingly effective at pulling CO2 out of the atmosphere and putting it into the ground. So it's another question would be, did the expansion of C4 grasses in the Indian subcontinent, are they responsible for pulling CO2 out of the atmosphere, which then allowed, you know, the ice sheets to form and all that stuff? So the question then is, what did CO2 do throughout the Neogene? And there are a lot of data on this subject, and I'll show you the most complete compilation that I could find. And you can see that for the Pleistocene, there's a lot of data with a lot of different kinds of proxies. So this is boron isotopes, diatom frustules, alkanones, and leaf stomata, which are supposedly sensitive to the amount of CO2 in the atmosphere. And you can see that the different proxies don't really agree with each other. There's huge scatter in them. And the period of the late Miocene, where we're talking about this transition in the Indian subcontinent, or at least first discovered in Pakistan, is in this time interval. And there's lots of different proxies. There's not a whole lot of data, and they don't agree with each other. So the proxies don't agree with each other, and they're poorly calibrated with respect to age, and so we don't know what CO2 did in this time. I just challenge you to tell me, please, somebody tell me what happened to CO2. So I don't know the answer to that, but it is a solvable problem. But obviously nobody was interested in this time interval because they're all focusing on the mid-Miocene climatic optimum that I showed you earlier. There's a lot of data there to show that there was more CO2 in the atmosphere during that warm period when there was very little ice. And then this is the Pliocene and the Pleistocene. And So people have been focusing on that, but nobody was focusing on this time interval, and so we just don't know. So what came first, CO2 drawdown, if that happened, or the C4 expansion? And interestingly, our story begins and ends in the oceans. Back in 1979, Lloyd Keigwin from the Woods Hole Oceanographic Institution was studying deep sea cores, and in fact, these two green ones, the stars, 310, these are deep sea drilling project cores that came from here, and he found this mysterious shift in stable carbon isotope ratios in the Pacific, and he dated them based on the first appearance of a fossil named C. primus at the time, and that had been tied to magnetostratigraphic horizon that was dated at about 6.2 million then. A lot of people, Edith Vincent, and she found the same thing at the Pink Star, which is here in the middle of the Indian Ocean at 238, and it was tied to the same biostratigraphic marker. And then Bilal Haq et al. In 1980 compiled data from all these little stars. The little stars, not the big stars. The white, green, and pink stars. He found the same shift in every ocean, and he associated it with the first appearance of something now called Amaryllis, which is the same thing as C. primus. So biostratigraphers changed their mind about what to call it, and it was found in what they called Epoch 6 at the time, and was dated at 6.2, and so they dated this transition at about 6 million. So I'll show you an example of the data from the time. So this is DSDP whole site 238, and this is the Delta C13 data, and you can see this shift that happened just after the first appearance of this guy called Amaryllis primus. So a few meters up, and then this is the Delta 18 data, and so this shift in carbon isotopes is the shift that I showed you in the Zakos compilation slide, called the Late Miocene isotopic shift. So how does that relate to the C3, C4 vegetation shift that Quaid et al. Found in Pakistan? So since Quaid et al. 1989, we're working in Kalialkas, among other places. There have been many studies on carbon isotopes from the continents. This is a compilation by Latour, 1997. This is the Pakistani record that I showed you before from one of the sections. So the transition was thought to happen about 6 million, and then there's some others. East Africa is much later, so the earliest shift, according to these data, it was in Pakistan, and then it looks like the Nepali record was a little later, and then East Africa was way up here, the North American. So I got interested in how were these, what was this timescale based on, and how did it relate to the marine record, which didn't have any magnetostratigraphy, because those were DSDP cores and you just couldn't do it then. The records were too bad, the sediments were too disturbed. So there was another compilation by Seema Singh et al. Who compiled a bunch of data. This is the Patois Plateau of J. Quaid and others, and then there were these other sections that were, and they all had dates 7, 6, 6.8, 7.4, something like that. So it looks like, are these all the same date, and this is just the uncertainty in the placements of things, or what? And then East Africa, maybe it was a little earlier, and North America, maybe a lot later, and South America, maybe about the same age. So what were these? These are the references. So I just want to show you what timescales were used in calibrating these different records. So the present study used the Mencken and Dalrymple 1979 and Lebrecht and Candy 1977. This was based on the Candy-Kent timescale and Bergen, Kent, Flynn, and Vancouvering 1985 timescale. So you see, there's just a bunch of different timescales that were used to calibrate these sections, and North America had no magnetostratigraphy whatsoever. East Africa was using, Central and South Africa didn't have any magnetostratigraphy to speak of. There is some, but they didn't use the best magnetostratigraphy in these studies. So all these different timescales, you'll recall that I've been very careful in my terminology. I said that we called it Epoch 6 then, and it was thought to be 6.2 million then. So what are the temporal constraints for the data? The dating in the marine sediments was based on the first appearance of Amaryllis, which was tied in a couple of records to this thing called Epoch 6. The dating in continental sections was based on magnetostratigraphy or fossil identifications, which were indirectly dated by either potassium-argon, argon-argon dating, or magnetostratigraphic timescale. But the different studies used different timescales, and some were just relied on biostratigraphic calibrations from elsewhere. So what's the effect of the timescale calibration alone? So the magnetic timescale. So I find this figure hilarious. This is this Epoch 6, which is now called C3AR and C3BN, this little normal zone, this pair, and this is C3BR, and this is C4N. This is the big long normal, which was then called Epoch 9, is now called C5N. So if I just take this one reversal that's common to all the timescales, it started out about 6.3 million in Lebrecht, Kent, and Candy, 77. And the age has migrated down to 7.6 in the last timescale. So just from using different timescales, you get 1.5 million years difference in the age, in your interpreted age. Just from the timescale. Has nothing to do with the age, it's just the timescale calibration itself. So that's not good. That means that a lot of this interpreted synchronicity or asynchronicity could be just from different timescale calibrations. So so we have to go back to the original data and directly tie the magnetostratigraphy to the C3, C4 isotopic, the delta C13 data, and recalibrate everything to the same time scale. And I've picked the GTS 12, which is, it's pretty stable by now. There's just small changes going to the most recent one. So we're going to stick with the Grasslands et al. 2012, geologic timescale and magnetic timescale. And then we need to tie the deep sea records, all those deep sea records, that somewhere there has to be a core that has amyrolythus, magnetostratigraphy, and carbon isotopes. And I know of one core, one international ocean drilling project, a program core that has those three things. And then extend the analysis to all the deep sea records that have amyrolythus and isotopes, and then we'll circle back to other marine proxies and we'll just see what the story is after we get through with this housekeeping exercise. So I'm going to start back up here on the Indian subcontinent. These are the Pakistani records, Kali-al-Khas, Jalalpur, Rohtas, and then in India, the Jwalamukhi and Haripur Kolar. And then in Nepal, there's two other sections that have magnetostratigraphy and delta C13 data that can be tied together directly here in Nepal. And then finally, I'll show you data from this core, which was taken in the off the coast of India, which is the Rosetta Stone. It has all three of these data sets. So recalibrating isotopic data, what I do is I first digitize the magnetostratigraphy in height coordinates, so meters above some arbitrary zero level, then relocate the isotopic data, which was always reported in terms of age. And so they have to be relocated in terms of height, and then find the bounds of the transition in the magnetostratigraphy, and then recalibrate all the records to the Grasslands et al. Timescale. So here's a data set I showed you before. The open circles are the Kali-al-Khas. This is the Jalalpur data from Quaid et al. 1989. And then the magnetostratigraphy that was used to calibrate this. So this was the magnetostratigraphy came from Noy Johnson et al., published in 1982. And so if this is the latitude of the virtual geomagnetic pole. So if it's over here in positive territory, these are normal sites. And if it's over here, these are reverse sites. And there were some tuffs, volcanic tuffs that were dated. And these are the formation boundaries. This is this long normal I talked about before. And then up here, you can see that the section was severely undersampled, but you have some kind of magnetostratigraphy. And using these volcanic tuffs, they were able to tie this to a very distinctive part of the timescale, and then this guy to a very distinctive part of the timescale. So this is from their paper, the Johnson et al. Paper. It was calibrated with the Lebrecht-Kenton-Candy timescale, 1977. This was called, it's still called the Gauss, and then this is was called EPIC 9, and it's now this C5N. And so this is a pretty good calibration, and this is a pretty good calibration. The rest of it, I think this must be this, Cron 5. It's a little undersampled, so it's not it's not really certain, but I tied it to the time scale. Here are the chron boundaries. We now call these crons, not epochs, and they have different names, but this is the Gauss, this C2AN, and this is this C5N. And then the ones that are in parentheses were reinterpretations by me in my paper, and so then the isotopes can be placed on a height scale, the same stratigraphic section. You can see here's the C3 plants. These are all C4. The transition must have happened between here and here in height, and so I did this consistently. And so now we can apply these ages to these data. So I did that for all of these sections. I'm going to show you the data. I'm not going to show you each of the individuals. So here's a compilation of all the stuff that I did. This is the Jalalpur section that I just showed you. The green triangles are the isotope data, so the shift occurs between these two cyan boundaries. These are the timescale picks that I just showed you, and then these are all the other sections. I don't expect you to be able to understand this, but this is this first section that I showed you, the Kali-Alkas section, where the tie to the timescale is rather straightforward because it was sampled so densely. And then using the ages that are then inferred from this diagram, we can plot the transitions, each of those dated transitions, against age and height, the height of each of those transitions against its age, and then fit a polynomial through it to get a kind of a sediment accumulation rate, and then tie the dates from that to the isotopes. So these are the boundaries that I marked in cyan in the last figure. So this record, you can see the transition occurs somewhere between there and there. So it must have been around 6 million. This one, too, had to happen around maybe 6.5 or something. And this is the Jwalamukhi record, and transition occurred between here and there. So somewhere between 6.2 and 8.5. And so I've split these data into the Indian and Pakistani records, which all have the transition occurring somewhere between here and here. This is the Kalial section that I showed you before. And then the Nepali sections must have happened much later. So here are the data, the isotopic data from that summary slide I showed you before, all tied to a common timescale. And what I was hoping was that it would all just collapse into one neat picture. But of course, there's a range in the possible ages. This is the Kalial section here. And so I've just drawn a black bar. This transition must have occurred between here and there in India and Pakistan. And you can see that that must have been earlier than the Nepali records, which had to have happened between here and here. The Suraikola record looks the neatest because this one goes over to C4 and then goes back. I don't know what that's about, but this record, the Suraikola record, suggests that in Nepal the record the transition must have been younger than the one in Pakistan and India. And then, so what about Argentina? I told you before that South America was supposedly transitioning at about the same time, but Latour did carbon isotopes from a section here in South America called the Puerta de Coral Quemado, and the magnetostratigraphy was done by Bob Butler in 1984. So here's the same kind of thing. Here's the timescale interpretation, and these are the isotopes, and you can see the transition occurs way up here just in the Gauss, so 3.5, 4 million. There's a gradual shift that starts earlier, maybe around 9 million, 8.5 million, but this profound change to C4 dominance doesn't happen until about 3.5 million years ago. So it's not globally synchronous, and it's a gradual shift starting at about 8.5, and that's, you get the same picture from ODP cores 763 from near Australia using leaf waxes, and from Andre and from Tauxe. And so there's a lot of evidence that Australia and South America transitioned much later. So how does this C4 transition in northern Indian subcontinent relate to the late Miocene carbon shift of Haack et al. 1980? We need a record with magnetostratigraphy, carbon isotopes, and the first appearance of amylolysis. And you would think that would be easy with the thousands and thousands of cores that we have, but it was not. There was an expedition from the International Ocean Discovery Program in 2015 that went to here. We drilled 2 sites, and the title of our expedition was the Arabian Sea Monsoon. I wanted to go because I had worked here early in my career, like I said, as an undergraduate. I had sampled these sections, and this is the Indus River, you know, comes down, and this is in the outpouring of the Indus River in the Delta, and so I thought, well, it might be fun to see what's happening in the ocean and compare it to what was going on in the land. And so so we did drill it. It was tough going, very exciting cruise. We got a lot of sand in this unit, and then, so basically we had 2 styles of sedimentation. There was these sandstones, big sandstones, and very discontinuously cored because it's very difficult to recover sand. And it appears from the biostratigraphy that the sandstones were deposited at an extremely high rate. And then it was these big turbidite units were separated by more calm deposition called Hemi pelagic sedimentation, with a much lower sedimentation rate, and we have a nice calibration from both magnetostratigraphy and so these triangles are paleomagnetic tie points, and this is a calcareous nanofossils in here. So we had a couple of those, and then one plankton foraminiferal date here. And then very rapid deposition here, and then slower deposition. And so when I was out there, I thought it'd be fun to look at the leaf wax data and the carbon isotopes. And so the graduate student who was out with us, Hannah Liddy, did this for her PhD thesis under the supervision of Sarah Feekins at the University of Southern California. And so, according to Warney and in Sarah Feekins' companion paper to mine, you have the leaf waxes from this interval in here were from peninsular India, and these sandstones came from the Indus River, based on something called the BIT index, which indicates whether it's marine dominated or continental. And so the hemipelagic, the leaf parts blew from peninsular India to this and were deposited in these sediments. And so when we look at the C3, C4 isotopic data from this interval, it's from peninsular India. So that's a zoom in of this. I'm going to show you this interval in here. Here's the magnetostratigraphy. Anybody who knows magnetostratigraphy knows how disappointed I was, but I do think that we were able to correlate into this time interval. So this is what used to be called Cron 6 and is now C3BN, this thing, which has been tied, and we found the first appearance of Amaryllis, and that has been tied to being right before this particular reversal. So I'm interpreting this reversal as C3BR.2R. And then there's another fossil called Nyclithus amplificus, which was found here. And so these all constrain the magnetostratigraphy. You can see that the transition occurs right there. Here are the isotopes. These are C4 isotopes, these are C3 isotopes, and so the transition must have occurred sometime in this interval. And so that's the same time as in Pakistan. Great. So now let's go look around. What about Africa? There were many papers from East Africa. None of them have tight magnetostratigraphic chronologies, very sad. However, there are some DSDP ODP cores off the coast of Africa which have Amaryllis and have leaf waxes that have been analyzed. And they also have another fossil tie point called Hamatus, Disc West, or Hamatus, has a first occurrence at about 10 million. So we have some constraints from these cores. I picked the ones that had Amaryllis in them. There's one here. I was also on this cruise, and unfortunately the magnetostratigraphy just was terrible in this interval. And so none of these cores have magnetostratigraphies. This is 235. We talked about that before. It had the Amaryllis datum here. And so in this East African core, the data of Polisar et al. Show this is the C4 isotopic expected value. This is C3. So it transitions from C3 to C4 sometime after the first appearance of Hamatas at 10 million. But you can see it happens before the Amaryllis first appearance. And so this suggests that this transition in East Africa happened well before that in India and Pakistan. And but in the Indian Ocean over here, you can see it happens just after the first appearance of Amaryllis, which is this dotted line. And so this is consistent with the Indian Pakistani data and the data from 1437, whereas these data make it that East Africa probably went first. So now we have magnetostratigraphy and amaryllis primus. Was the C3-C4 transition globally synchronous? No. It happened first in, I'm sorry, Western Africa, not Eastern Africa. Western Africa, then in India and Pakistan, then in Nepal, much later South America and Australia. So as predicted by that modeling exercise that I showed you in the beginning, there's no reason to think that even with the same CO2 everywhere that this transition would happen at the same time everywhere. So what was the cause? The short answer is it's complicated. The ideas that have been proposed are changes in precipitation, like the monsoon, because C4 plants like drier climates. But Feekins et al., in her paper, she found that there was strong evidence for increased fires, but those were grass fires of the grass that we know is there, and there was no change in precipitation. She did hydrogen isotopes and found no change in precipitation throughout that entire section. Was it cooler because C4 plants like cooler climates? Well, Feekins found from Tauxe 86 that there was a long-term cooling trend, maybe. So maybe it's cooler, things cooled, favoring C4 plants. But what caused the cooling? Was it tectonic uplift of the regions? Or was it a drop in CO2? Or was there a decrease in CO2 because C4 plants like lower CO2? So C4 plants like lower CO2, they like cooler climates, and they like drier climates. So which of these things drove the change, the vegetational change? What if there was a change in CO2? What caused it? The original Penguin idea was that there were some changes in ocean circulation. I don't know, he didn't specify. Was it increased weathering, like Mo Ramo would like? Or did C4 vegetation itself pull CO2 out of the atmosphere and provide a positive feedback loop? Because this wasn't globally synchronous, that's a harder argument to make. I thought it was cool, but it may not be the answer. So the conclusions are that Paleosol carbonate nodule records from northern India and Pakistan are consistent with a 7.4 or 7.2 change vegetation shift. Nepal's transition was later. The DSDP core, or the IODP core I showed you, serves as a Rosetta Stone, and it shows that peninsular India had a shift at 7.2 million, and Africa was likely earlier, but the jury's still out, as there are no magnetostratigraphically calibrated records. Argentina is much younger, and the ocean carbon shift and continental C3-C4 transition could be roughly coincident with a drop in PCO2, but other proxies disagree. So something may have caused a drop in CO2, I don't know, but the C3-C4 transition on the Indian subcontinent could have amplified the CO2 drawdown and encourage and spread the C3-C4 transition all across the globe. My talk. So, questions?
Great, thank you very much, Lisa. It's a sort of a, like you say, a complicated story with a variety of angles, and it's fascinating to look at the interplay between the marine record and the continental record. And I think that we've learned a lot over time from our oceanographer colleagues, and I'm delighted that you're sort of straddling that interface. It looks like
we have a question.
Kay has a question. Kay, is that you?
It is. It is I.
Hi, Kay.
Hi.
Long time no see.
Yeah, I've read the Feekins paper, but I can't remember whether it's the average precipitation that she says hasn't changed and how that's measured. And the question is that monsoons are a matter of seasonality too.
Right. Yeah.
So yeah.
You should ask her all those questions, but so she used hydrogen isotopes to detect changes in rainfall. I think it's a proxy. And what she was looking for were averages through time. What she did find, which is interesting, was increased evidence of wildfire. Mm-hmm. Like these grasses, the little leaves that they were looking at would be burnt. So they're, but of course, if you have more grass, you're going to have more grass fires. So that doesn't mean that anything about temperature or rainfall or anything. But so it's averages, and it's done with hydrogen isotopes.
Okay.
Yeah.
Yeah. Thanks. I'm not giving up on the monsoons.
Well, good. That's fine. Hi, Kathy. Unmute yourself.
Please unmute yourself.
Great. Can you hear me now?
Yes.
Yeah. Mukhtiar has the controls. I love that, being controlled by people in Pakistan. So Lisa, it's great to see you. I have more of a comment. It was very interesting to see the difference between the timing in Pakistan versus the timing in Nepal. And you seem surprised by that. But I'm not. I think at least the paleontologists are not surprised, because we have a number of faunal indicators that change earlier in Pakistan, later in Nepal, and sometimes we even have intermediate records from Harry Talayangar in India that suggest that there's a kind of a big time transgressive shift that's in ecosystems that's slowly sweeping from west to east, possibly starting in the Mediterranean, all the way to Southeast Asia, where we now have the remnants, the faunal remnants of the Sewalic faunts. So I found that actually very consistent with what we've been able to see from our paleo records.
I guess we should talk more.
I'm for that. That sounds great.
Yeah. Oh, that's interesting. That's great. Also, I gave a talk like this a few years ago in China. I was in Beijing, and they have wonderful magnetostratigraphy there. I mean, it's just the best. These continuous records, and they just sample the hell out of them. It's gorgeous, and they showed me their isotope records. And they do the opposite thing. They switch from C4 to C3 at this time in north of Tibet. Now, they haven't published it as far as I know. Maybe they have by now, but I was urging them to do that, because it's better magstrat than we've got, and extremely carefully done. And it's another part of the story, right? It's the other side of the mountains.
Yeah, another thing, I see that Doug Burbank is in the seminar tonight, and I found some really interesting points in his talk about 2 months ago. And he made a point about, he was looking at the storm tracks coming in off the Bay of Bengal, sweeping along the southern margin of the Himalayas, and he mentioned that wherever the greatest rainfall is depends on the height of the mountains, which is changing over time. Sometimes it's to the east, sometimes. And so things like that could also be affecting not the amount of precipitation as well as its seasonality. And I'm not sure we'll ever have the adequate information, independent information, to know what those scenarios were, but they might be, they might also be part of the reason that we're getting these heterogeneous signals.
Mm-hmm. Yeah, because you don't know the elevation, and I don't know whether it's important, but Nepal is further south than these things. I don't know if that's important or not. I don't know why that would delay it. But yeah, so good, cool. Nice to see you, ladies.
Yeah, likewise.
Wow.
Yeah, for our Pakistani colleagues, we all used to have tea together on top of the core rest house.
Did we? I don't remember that.
I have a slide of it.
Oh, yes. I remember.
How come I don't remember that?
What was
I don't know.
Well, I'll send you, I think I have a scanned image. I'll send it to you, Lisa.
Okay. Yeah. Okay. Well, we did have fun. Then.
We did indeed.
Yeah, and it's great to see all this put together too, and that you're still, you're still after it. So, but I guess, the idea of,
I'm out. Tauxe out. I'm working on the intensity of the field strength now, and that's what I'm doing. But I had to do this.
I'm glad you did. But I mean, the global change in CO2, it really doesn't fit at all.
Well, we don't know what it did. I mean, those data are crap, right? We don't know what it did. And there's hardly any data. They go after the early Miocene. They love it. The paleoceanographers I'm talking about. And then they love the Pleistocene stuff. And then this interval that we're interested in, this upper Miocene bit, there's a few studies. That's it. And they don't agree. And I don't know.
So Lisa, let me follow up on that and just ask you, is there a potential for getting additional deep sea core material out of the Indus cone that could expand on the data set that you've got? In other words, the records should be there in the marine environment.
Yes. And it should be possible to get, now these were most of the isotopic data that I showed come from the old DSTP cores, and you don't get magstrat out of those. I mean, they're just too discontinuous, and the cores were just totally screwed up. So they're you're not gonna get there from here. So the newer ones that were done with the new technology like we had, we could do this. And there are a bunch of cores around India, but I'm not sure how many have really good magstrat. I mean, it was a struggle in these for a variety of reasons. One of which is Peter just wanted to drill this damn slump. It just kept going, and it was like useless to me. So I don't know. And we did it twice. So yes, I think that there are other records that could be had there. So make a proposal to the IODP.
Yeah, I mean, I think that I've seen some pretty good data coming out of the Bengal fan over on the mouths of the Ganges, and I think that the time will come when we get a good record out of the Bay of Bengal and a good record out of the Indus, and it may be that our continental records are maybe discontinuous and patchy, but I think that the marine records are, in many cases more complete and sort of have maybe a more homogenizing signal in them. So
Well,
I would.
yes and no, but then look at that record that I showed you. It's not continuous. There's these huge,
Yeah.
big slumpy things, and
Yeah.
then there's a hemi-pelagic unit, and so I actually think that we could do a much better job in India and Pakistan by sampling denser and using taking multiple samples per horizon and throwing out the things. 40% of my data are random, so you should not be using those. You should not. I think if we went back and sampled like every 5 meters or 2 meters or something through these intervals, we could do a much better job than and co-locating the isotopic records with the magnetostratigraphy.
No, I agree, and I think that just pointing some direction into the future, I think that the sequence stratigraphy and analyses of the morphology of these huge cones of debris on the floors of the Indian Ocean you could probably find places where you didn't have big thick slumps, and you could probably find places where you've got finer grained, more continuous records, and I suspect that some of the answers are there to be found if we can core the correct places on those cones.
Well, the 90 East Ridge has some beautiful records, magnetostratigraphies possible. It's actually pretty nice, because you're up above where all the crap is coming down.
Yeah.
No, I'm sure it can be done better.
Well, I think there's some opportunity for students there to look at this, the proverbial source to sink story, and we've got a lot. We've got a considerable amount of the information available, but it's going to require some additional information and then some elegant integration to put it all together. And I think these are challenges for young people today. It'd be wonderful to pursue, and it does sound like some more ocean drilling might be extremely useful.
Yeah, count me out. I've done 5 of those cruises, and God, the last one was down in the Scotia Sea.
Okay, everybody. Well, I think unless we see more questions, we're pushing Kay and Badger into the 2:00 a.m. time frame here, I think. So we're very grateful for people staying awake on this side of the continent or the nation of the globe, and we're welcoming people in Pakistan and India in the morning. And those of us in the Western United States are looking forward to a beautiful lunar eclipse later on this morning. And thank everybody for your participation. And next week we're going to have Peter Zeitler's talk, so you'll be seeing the flyer coming out very soon. So
cool.
Okay.
See you, Badger K.